Hey guys, and welcome back to Mathematical Statistics. This is the second video tutorial on some fundamental properties of the expected value and variance operators. One thing that doesn't get a lot of attention is looking at the values of which the expected value operator is, I'm calling it an operator, but the expected value is defined on. So let's just jump in and we will see what happens. So let's suppose we have the variable x and it has CDF 1 minus x to the negative alpha. So I assume you guys know from Intro to Probability Theory that d of x, so I write derivatives as d of x, which is taking the derivative with respect to x, just because I don't like d over dx. It's too much notation for me. So 1 minus x to the negative alpha. We know that the derivative of the CDF is just the PDF, right? So dx of 1 minus x to the negative alpha is what? That's just alpha x to the negative alpha minus 1, right? Great, so we have the expression for the PDF. So what about the expected value? Well, we know, let's write it like this because I like to do things step by step. X in the support of the density function of the random variable x times x times d of x. Great. Okay, so what is our support? Excuse me. Well, we know that our support is for x values greater than 1, so we can just plug that in right away here, and we can say that the expected value of x is the integral from 1 to infinity of there we go, of our density times x times dx. Okay, so we know the expression for our density that we got by taking the derivative. And LaTeX does not like me today. Okay, good. So let's plug this in. Density of the derivative. Great. Okay, cool. So now we can pull the alpha out, right? Because that's not a function of x. And we can also combine this x we can absorb this x up here, right? And get rid of this negative 1. So we can do that by just deleting this x here. And we already pulled out the alpha, so let's get rid of this. Cool. Okay, so now we have a pretty simple expression. We can just go ahead and evaluate this integral. So I like to do integrals by just thinking about it backwards. So what function, when we take the derivative, would give us x to the negative alpha? Well, let's just think about it. So we know that if we take, so first of all, we know that there's going to have to be an x to the alpha minus 1, right? Excuse me, plus 1, because we have to subtract 1 off of that. Negative alpha plus 1, because we have to subtract 1 from this to get x to the negative alpha, right? Because when you take the derivative, you subtract 1 from the exponent. And we also know that there's going to have to be some normalizing constant here, because when we pull this guy down, we're going to have to divide through it to make sure that it disappears in here. So let's just write that as alpha plus 1 to the negative 1. Okay, cool. And that's it, right? I think that gives us our derivative. Yep. Great. So, except this is now evaluated at 1 and infinity, right? Okay, so as x goes to infinity, this is a negative exponent, right? So this is going to disappear. And when x is 1, this is just 1. So our expression for our expected value just becomes alpha. Okay, cool. When is this not defined? Pretty simple, right? If alpha is negative 1, then negative 1 plus 1 is 0, and 0 to the negative 1 is undefined, right? Well, something divided by 0 is undefined. So any alpha that is greater than -1. Did I do this wrong? Yeah, I did. Excuse me. This should be negative alpha, shouldn't it? This should be negative alpha because we have this negative alpha up here. So let's make that negative alpha. So let me back up and then say any alpha greater than 1 is going to be, it's going to have this expression defined. So alpha cannot be equal to 1, right? Cool. So that is it. We got the expression for the expected value, and we know that. Let's just write this out. For alpha not equal to 1. Okay, cool. Now what about the second part, variance? So I'm sure you guys know this, but when you calculate the variance, you always want to write this down. You don't necessarily want to use it. Sometimes there's some simplifications you can make, but you always want to at least write this down just to think about it. And since we're using the actual definition of the expected value, we usually want to calculate e of x squared because we can pretty easily do that. So all I did here was just calculate the expected value of x squared. And I pulled it in here to, by law of the unconscious statistician, or LOTUS, which I assume you guys have seen from introductory probability and statistics. So you can pull in the x squared here, and same limits of integration, and this is our PDF that we've seen before. So this is almost exactly the same integral, right? Except for instead of this guy, we get negative alpha plus 1, right? Because we already we added 2 x's here instead of 1 x up here. Okay, so now we just need to find the let me scroll down. Now we just need to find the derivative, the integral of x to the negative alpha plus 1. So just like before, we know that that's going to have a, get rid of this integral sign, that's going to have a plus 2, right, in order for it to become plus 1 when we subtract by 1. And since we don't have anything out front here, we need to make sure that negative alpha plus 2 is in the denominator, right? So let's just copy this, and just like before, we're going to have to evaluate at 1 to infinity. The same arguments apply. We have a negative alpha here, so that goes to 0 when x goes to infinity, and it goes to 1 when x is equal to 1. So now we have the exact, these should all be e of x squared. So now we have the exact expression for the first part of the variance. Don't forget that the variance, when you calculate the variance like this, you always have 2 parts. So the variance of x is equal to this minus this squared, right? We can write that squared as negative 2. Okay, so this is the expression for the variance in terms of alpha, which is our, the parameter of our distribution. So cool, great. So what values is this not defined for? Well, we can see this not defined for 2 and for 1. So for alpha, because then you get division by 0, which is pretty much all you're looking for when you're thinking about what values things are not defined for, especially when you're talking about specific values. Cool. So we just did the variance and the expected value of a random variable by starting with the CDF and differentiating and plugging into our definition of expected value. So we're going to keep going on some problems like this in the next video. Thanks a lot.